In this video, we solved problem number 3 from the second quiz in the spring 2021 semester in the elementary differential equations class at Tulsa Community College. Now, there were multiple forms of this quiz, so this may not have been your problem number 3, but this was one of the problems that was featured on quiz number 2 this semester. So the problem statement says, show that the differential equation is exact, then find an implicit solution to the differential equation. So we've got a function of x and y times dx equals a function of x and y times dy, and that equals 0. We typically label this function m of xy in our class, and we label this function n of xy, of x and y, if the partial of this function with respect to y is equal to the partial of this function with respect to x, then the differential equation is exact. If you're wondering, like, how do you know which one you're supposed to take the derivative with respect to, which variable? If you're having trouble with that, it's always the opposite variable of what's there. So if you see a dx here, you want to take the derivative with respect to y. If you see this times a dy, you want to take the derivative of that function with respect to x. So the way we'll start this is we'll compute those partial derivatives and then show that they're equal to each other. Okay. So I've got a product of two functions of y here, first function and second function. The derivative of a product is the derivative of the first times the second plus the derivative of the second function, which in this case is 1 over y, times the first. And of course, the y's reduce there. And we just have natural log of y plus 1. And then here, the derivative of e to some power, and if that power involves this variable, is e to that power times the derivative of the inside with respect to y, treating x as a constant, which is negative x. Now, that rule will hold even if there is no y in that, but if there is no y, I would tend to think of it as a constant first and then immediately say it's constant with respect to y, and therefore it's 0. But if this involves this variable, you say e to that power times the derivative of the inside with respect to this variable, holding the other variable constant. The derivative of a constant times y is the constant. Okay, and then 3x squared does not have any y's in it, and we're treating x as a constant here. So the derivative of this constant with respect to y is 0. You almost don't have to write that because adding 0 doesn't do anything, right? Negative 1 times negative x is a positive x. We have that. So that is the partial of m with respect to y. Let's see if the partial of n with respect to x is equal to that. If we've done everything correctly, it actually will be. Or not if we've done everything correctly. If the problem is set up correctly, it will be, because we're supposed to show that the differential equation is exact. We're not asked to determine whether it's exact. So as long as it's a well-posed problem, and they're actually asking us to do something that can be done, then we should get the right thing from this. So we want to take the derivative of n with respect to x. That's the partial derivative with respect to x of this. Now, this piece is already in a great form to take a derivative with respect to x, because I've got a function of y times x there. Now this isn't. I've got a y squared in the denominator, and this might be simpler to, or the derivative might be simpler to evaluate if I actually split this up a little bit. So I think I'm going to do a little bit of algebra before I take the derivative this time. So we'll bring out the negative e to the negative xy. And now I've got this sum divided by y here. I just want to take each of the pieces and actually do the division. I'll have xy divided by y squared. And one of the y's will reduce. And then I'll have a 1 over y squared over here. So that y reduces with that y. And the +2 is still there. Okay, so we have just done a little bit of algebra. We've rewritten this in a different form. And remember, we're taking a partial derivative with respect to x. Because we're taking a partial derivative with respect to x, let's take this guy and distribute it over that sum there. I know I could have done that in that last step, but I just thought of it, so I'm going to do it now. And I think I'll write that as a quotient. And then if we distribute that, I'll have the negative e to the negative x y over y squared here. And don't forget your +2. Okay, so now we're ready to take a derivative with respect to x, treating y as a constant. Now you didn't have to simplify first, but since we were about to take the derivative, it was easier if we did a little bit of algebra, prepare to differentiate. Okay, now I've got a function of y times x. We're treating y as a constant, so this is a constant times x. The derivative of a constant times x is just the constant. So we bring the constant down. Okay, here, the y is a constant, so I can bring out the -1 over y as a constant. But this, in the numerator, is a product. I've got a first function and a second function. So according to the product rule, we should have the derivative of the first function times the second function undifferentiated plus the derivative of the second function, derivative of x with respect to itself is 1, times the first. And I wrote that there because I didn't want to be distracted by my product rule. Now that I've done the product rule, I can just look at this and remind myself, or what I've written down will remind me that I want to take this derivative now. I haven't actually taken the derivative yet, but this says take the partial derivative with respect to x of this. Well, the derivative of e to some power is e to that power times the derivative of the inside with respect to x, treating y as a constant. So this is a constant times x. The derivative of a constant times x is the constant. Okay, so that's this piece. That's just this one piece. We took care of this piece and this piece. Now we have to do this one. Again, the negative y squared, the -1 over y squared is a constant. And then we have this e to the negative xy there. The derivative of e to the negative xy with respect to x, treating y as a constant, is e to the negative xy times the derivative of the inside with respect to x, treating y as a constant. So we have negative y there. And the derivative of 2 with respect to x is, of course, just 0. And so this is it. Now remember, it's supposed to look like this. We're trying to get it to match this. So if it doesn't match this, something went wrong. Now initially it looks like it doesn't, but perhaps after some simplification it actually does. So let's do some algebra and see if this is what we need it to be. Got -1 over y here times negative xy times the exponential plus the exponential. And then here, the negative and the negative will reduce. So we'll have a positive and one of those y's will reduce. So we have a +1 over y times the exponential here. And let's distribute next. Negative times a negative is a positive and the y's will reduce. And then we'll have a -1 over y times that exponential plus 1 over y times the exponential. And we've got that. So we simplified to prepare to differentiate, and then we differentiated using a lot of product rules and chain rules as appropriate because of the exponentials and because of that sort of beast of an expression that we started with at the very beginning. All right, so now let's compare this to what we have over here. Do you have natural log of y plus 1 plus x times the exponential? Yes, so that's great. So we know that since these two guys are equal to each other, the DE is exact. And then there's going to be an existence statement about a function, a function f of x, y. Okay. Now remember what it means for a DE to be exact. If the DE is exact, that means there exists a function f of x, y, such that the total differential, or the exact differential of f, is equal to the left-hand side of that differential equation. So we've got m dx times n, or plus n dy. And by definition, the exact differential, or the total differential of f, is the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. When you're solving these problems, I like to see the existence statement, because that tells me that you actually know what an exact differential equation is. An exact DE is exact if there is some function out there such that df is equal to the left-hand side of that differential equation. Okay, so now we just want to find f. And finding f can be done pretty easily, because if these two expressions are equal to each other, these two functions must be equal, and these two functions must be equal. So we must have that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n. We need to find f. In order to find f, if I have the derivatives of f with respect to x and y, well, all I have to do is anti-differentiate with respect to x and y to get f back. Now, because these are partial derivatives, each partial antiderivative only recovers f partially. So we kind of have to do both and then compare them to each other to make sure that we get the whole function f of x, y. So we've got our existence statement. We know that this is true, and now we're going to find f by anti-differentiating. So first we'll say that the function f is the antiderivative of the partial derivative of f with respect to x with respect to x, because those two operations are going to undo each other, and it's going to give us our f back. So we know the partial of f with respect to x is equal to m, which was actually quite a beast. We've got that. And f is the antiderivative of that with respect to x. And now we're treating all the y's as constants here, just like when we take derivatives, we treat one variable as a variable and treat all the other variables as constants. We're doing exactly the same thing here. So we're treating x as a variable and y as a constant. So even though this is sort of involved looking, it's actually not that involved. It doesn't involve any x's. So this is a constant. The antiderivative of a constant with respect to x is that constant times x. And then here, I've got e to some power, and that power involves x. A lot of students can get confused by this. Remember, y is being treated as a constant. So you want to think of this the same way you think of e to the kx. The antiderivative of e to the kx is e to the kx plus c, almost. If I were to take the derivative of something that looked like that, I'd have to multiply by k by the chain rule. Since we're anti-differentiating, we have to undo that. So rather than multiplying by k, we're going to divide by k. In this case, y is being treated as a constant. So our k this time is actually negative y. So we'll bring the negative down. The antiderivative of e to some power is e to that power. And then we have to divide by k, and k is negative y. And then we have the antiderivative of 3x squared with respect to x. Bring the 3 down, add 1 to the exponent, divide by the new exponent. And then you want to add a constant, but it's a function that's constant with respect to x, but not necessarily with respect to y. So we've got a g of y right there. And the 3's reduce. And now we have this. So we've got xy times natural log of y. Negative 1 over negative y is going to be a positive 1. So we have recovered f partially. We know that f is this function plus this function plus this function plus some function of y. We just don't know what the function of y is. In order to find the function of y, we need to do the same thing with the partial of f with respect to y. The partial of f with respect to y was much more involved. So I'm going to do a little bit of algebra first to that. The partial of f with respect to y, that was our n. That was x times natural log of y plus 1 minus xy plus 1 times e to the negative xy over y squared plus 2. Man, who wants to take an antiderivative of that with respect to y? We can do it. But yeah, it's going to be pretty involved, isn't it? X is going to be treated like a constant. If you want, you could distribute that x here. And then here, let's see, it'd be helpful to simplify this at all. We might write that differently. We might write that as xy over y squared, which would simplify to x over y plus 1 over y squared. All right, plus 2. Okay, so that's our f, or the partial of f with respect to y. So we need to anti-differentiate that with respect to y in order to get f back. As I'm writing this, I'm sort of bracing myself for the reality that this is going to take some work. That's okay. It's nothing we can't handle. Now, x is being treated like a constant, and we want the antiderivative of natural log of y with respect to y. That piece is going to require integration by parts. I'm just going to write that down. The antiderivative of this constant with respect to y is going to be the constant times y, no big deal. The same with this 2, it's a constant, so we're going to get a constant times y there. For this one, that's a little bit harder, isn't it? If I'm taking an antiderivative with respect to y, treating x as a constant, I'm thinking of this as an exponential times a function of y. I think I'm going to have to use integration by parts there as well. So I'm going to put 2 stars there to label that part of the integrand as an integral that I'm going to handle separately. And I'll just take a note to self that I want to use integration by parts there. Okay, so I've got the antiderivative of natural log of y. I'm just going to do this one and then this one separately, and then we'll put all the pieces together to find f. Bring the x down, or over if you prefer, factor it out. Now you have that. Now I'm going to think of this as the integral of u times dv. And if you have a logarithm in your integration by parts problem, that's always your u. dv is everything else. In this case, that's dy. The derivative of natural log of y with respect to y is 1 over y. We multiply by dy. The antiderivative of 1 with respect to y is just y. So we're going to get u times v minus the integral of v du. u times v gives me y natural log of y. And then we're subtracting the integral of v times du. Now careful here, you don't want to write natural log of y times, let's say y squared over 2. You don't want to take the antiderivative of this piece and that piece and just multiply them. You've got to simplify first. The y's reduce. Oops. So this is actually an antiderivative of 1. The antiderivative of 1 with respect to y is y. Then we're going to add, oops, not a constant of integration. It's going to be something that's constant with respect to y. So I'll call this, let's call it C1 of x. So it's constant with respect to y, but not necessarily with respect to x. So we've got that. Oops, that's there. And then that constant or that function of x is going to be over there. Okay, so that's that piece. And then we've got this other piece that looked like quite the beast. We got e to the negative xy times x over y plus 1 over y squared dy. I think I want to use integration by parts here as well. Now, typically, if you have a polynomial expression, you usually want that to be your u, but we don't actually have a polynomial in y. We've got y's in the denominator here. So that makes this a little bit more complicated. It makes it harder. But I think we should be able to use integration by parts. Let's see. Let's make this our u, and then make everything else dv. Now this actually may not work, but I think it will, so I'm going to try it. So I'll say u is this. Figure out what du is. dv is that expression. I'm about to anti-differentiate. So I'll leave this alone because the antiderivative of 1 over y is a natural log, and I know what that is. And then this 1 over y squared, I will write as a y to the negative 1 or negative 2, so that we can use the power rule when we anti-differentiate. So the antiderivative of this piece with respect to y is x times natural log of the absolute value of y. And the antiderivative of this piece with respect to y would be a y to the negative 1. We add 1 to the exponent and then divide by the new exponent. So we've got that there. Okay. And then the derivative of u in this case is the derivative of this with respect to y. So the derivative of e to some power with respect to y is e to that power. And then we're multiplying by the derivative of the inside with respect to y, treating x as a constant. And so this is a constant times y inside. So the derivative of that constant times y is the constant. So we have this times dy. Okay. All right. Let's see. Let's see if this actually works. I don't know if it is going to work. That does not look like it's getting simpler. It looks like it's getting worse. So we have u times v minus the integral of v times du. And I've got e to the negative xy times x, natural log of the absolute value of y. And then I'm going to have plus e to the negative xy times negative 1 over y. So there's going to be a negative 1 there and a y down here. So that's that. And then we're subtracting the integral of v times du. Ooh, I think that's going to be pretty bad. So we've got negative x times x is going to be a negative x squared times the exponential times the natural log of the absolute value of y. And then we'll have this times that. The negative times negative will make that a positive. We'll have positive x e to the negative xy over y there. Man, that looks worse. That looks much worse. So I don't think that that was the right choice for u and dv. Let's see, is there any other way that we could have thought about it? is your y is your variable. I guess I could have thought of this as my u and that as part of my dv. So let's try that. This is true, but it's not going anywhere. This is much more complicated than the original. So we're not going to try this, or excuse me, we're not going to use it. We tried it. It just didn't work out, and that's okay. Sometimes that happens. So we have this here. This is our u. Everything else is dv. So setting up my integration by parts table again, we've got u here. And if you want, you can write that as x times y to the -1 plus y to the -2. And then over here we have dv. We want to compute v. The antiderivative of this with respect to y is that. But then you've got a constant times y inside. When you anti-differentiate, you've got to divide by that constant. So you're going to divide by -x. Over here, when you compute the derivative of u with respect to y, we're going to get -x y to the -2 plus the derivative of this, which is -2 y to the -3. I was worried about that. Those exponents are getting larger. We got u times v minus the integral of v du. So we have x over y plus 1 over y squared times -1 over x times our exponential minus the integral of that, negative times a negative is a positive, times du. Okay. All right. And I think it's getting worse. We're not actually making it any better. All right, so we're gonna have to do something else. Let's think about this. Let's think a lot about this. We've got this integrand. And it looks like an e to the -xy times that. If we get a common denominator by multiplying that one by y over y, we end up with xy plus 1 over y squared down here. Now, it still doesn't look good, but if I maybe distribute the exponential everywhere, they've got xy times e to the -xy plus e to the -xy all over y squared. Like that kind of looks like a quotient rule. So it looks like a low d high minus high d low over low low. Do you remember that? Where the bottom function is y, because that's the bottom function squared. Or let's say it's the partial derivative with respect to y of something that looks like that. The question is, if that's true, if that's the pattern that we're matching, if the bottom function is y, what would the top function have to be? So this is the derivative of a quotient. And actually, this might not work. Just another hunch. This is where I would go next if integration by parts didn't work both times. Say, okay, kind of looks like a quotient rule. So what can we do from here? Well, we'd say, if this is low d high, the bottom function is y, so d high would have to be x times e to the -xy. And then we're supposed to have minus high times d low. So, and d low is just going to be a 1. So this is minus high. If minus the top function is equal to this exponential function, then -1 times the exponential function should be the high function, or the top function. Now let's think that through. let's actually use the quotient rule here. We have low d high, so we would get y times the derivative of this piece. The derivative of this would be negative e to the negative xy times the derivative of the inside with respect to x, treating y as a constant. So we would take this and we would multiply by, or derivative with respect to y, treating x as a constant, sorry. We would multiply by a negative x. So we'd have a negative x times a negative 1. It's going to be a positive x times e to the negative xy. That's the derivative of the high times the low function, good, minus high, which is this, times d low, which is 1. So yeah, this is going to work out. So this is actually the result of a quotient rule, and the derivative of the antiderivative is the original function. Now, I know that that was really hard and you weren't able to just use one of your methods automatically. You weren't able to just look at it and say, oh, U substitution, oh, integration by parts, oh, partial fraction decomposition. It wasn't that easy this time. This was a tough integral. And I pulled it from the book, but I think I pulled it from the section where you were just supposed to identify whether a differential equation was exact or not whether you were supposed to, or not from a section where the textbook authors were expecting you to solve it. So I'm sorry, this problem was a little bit harder than I had expected or anticipated. But the antiderivative of this is the antiderivative of this derivative, and the antiderivative of the derivative is this. Plus some function that is constant with respect to y, but not necessarily with respect to x. We have c2 of x there. Okay. All right. So now we can go back to this guy and sort of put all of our pieces together. The antiderivative, or excuse me, the function f is the antiderivative of that piece. And the antiderivative of x times natural log of y turned out to be xy natural log of y minus xy, plus a function of x, but we're going to tack that on at the very end, plus the antiderivative of x with respect to y, which is just x times y because x is being treated as a constant. And then we had minus the integral of this piece. Well, the integral of that piece, well, that piece was the derivative of this quotient. So the antiderivative of the derivative is that function inside, so we get that. But we're subtracting that, so we need to add, because we're subtracting a negative, we're going to add e to the negative xy over y there. And then the antiderivative of 2 with respect to y is just 2y. Now, if you're my student, you're saying, oh my goodness, that was really hard, and did you expect me to know to do that? I normally wouldn't expect you to do that. I'm not going to take off if you weren't able to evaluate that part of the integral. But hopefully, if you were able to infer that that's what it had to be, I'll probably give you some extra credit, give you some extra points for that. So this is our antiderivative of f with respect, or of the partial of f with respect to y with respect to y. But we need a constant of integration. It's constant with respect to y, but not necessarily with respect to x. So we'll call that h of x. Now this was f from the partial of f with respect to y. And then this was f from the partial of f with respect to x. We have xy natural log of y plus e to the negative xy over y plus x cubed plus g of y. So we want to see what matches here. Both of these are f, and those two reduce. Both of these are f. They have, this one has an arbitrary g of y in it, or not an arbitrary g of y, a g of y that we don't know. And this one has an h of x that we don't know. We want to use matching to figure out what g of y would have to be and what h of x would have to be. So after we have completed that, we've computed we found f in two different forms. We need to compare these to find f in general. Okay, that's the plan. So in general, we know that f has a term of the form xy times natural log of y. We also know that f has this term, and e to the negative xy over y. Now, I told you that I wouldn't expect you to be able to compute the antiderivative to get this, but we were able to compute the antiderivative to get this. So that was actually another clue for me that sort of messy expression was the derivative of this quotient, was because I knew that this quotient was supposed to come out. It was supposed to be a term in f somewhere. And since I knew that I was looking for something that looked like this, I was like, I bet that's that. And so that's how I knew to try to rewrite this guy as a quotient, or the result of a quotient rule, and then use that pattern matching to figure out that that was the derivative of this particular quotient. Okay, but again, I'm going to give you full credit even if you didn't think to do that. So these are the same. So those are in F. But these two pieces are not the same as these two pieces, or they don't look the same, but they actually are the same. This piece has to be equal to this piece. Well, the only way that works is if this function of x is x cubed, and this function of y is 2y. That's going to work just fine. Now there should also, be a constant of integration that's just a pure constant. So I guess h of x should be x cubed plus that constant. And g of y should be that 2y plus the constant. So our f of xy includes a 2y term and an x cubed term plus c. And you should always check it out, make sure it actually fits. Is f equal to this? Well, it's that plus 2y plus a function of x. Yep, it works. That's true. If f is this, does it satisfy that? Well, f is supposed to have that term, and x cubed plus a function of y, that 2y plus c is the g of y. So yes, and this is our function f of xy. Now that we have f, you want to state the implicit family of solutions. To this differential equation. And let's see. We were not given an initial condition. So the implicit family of solutions is this. It's f of xy, which is xy times natural log of y, plus this divided by y, plus x cubed plus 2y, equals some constant, k, and I'll let k absorb that c. Now, if you're saying to yourself, why is the answer f of xy equals k? You have to remember where this is coming from. Here's the idea. You're going to have some surface. I always draw it as an elliptic paraboloid just to make it easy on us. Could be any surface. This definitely does not look like that elliptic paraboloid. But let's say you have some function in general. Z equals some function of two variables. If we set that function equal to a constant, z equals k, we have this equation here. If we take the total differential of both sides, the total differential of f is the partial of f with respect to x times dx plus the partial of f with respect to y times dy. And the total differential of a constant k, given that k is supposed to represent a function of two variables, is going to be 0 times dx plus 0 times dy. So it's just going to be 0. This is the differential equation that we started with. That's our m dx plus n dy equals 0. So when we're solving an exact equation, we're starting, instead of starting here and differentiating or taking total differentials, which is a form of differentiation, right? Instead of doing that, we're just going the other way. So if we're going from here down to here, rather than going from here down to here, we're going to go from here back up to here. So that's why the solution is f of xy equals k. It's not just a function. It's a function of two variables is equal to a constant, because that's what we took the total differential of on both sides in order to get the differential equation in the first place.